for the introduction. Hello, everyone. Good afternoon. I'm Lei Zhangwang. I will introduce our work by the following parts, or make it quick because uh, some friends that were already introduced the basic information of lattice. Um, First of all, a lattice L is a discrete subgroup of an L-dimensional Euclidean vector space. And we can use this lattice space to represent lattice L. And lattice problems are about finding the short vectors and the closest vectors. For most lattice-based equation schemes like K-bar, their security are based on the hardness of LWE, which can be reduced to the unique shortest vector problem on some special constructing lattice spaces by using the Canon's embedding skill. And for most lattice signature scheme, lattice-based signature scheme like DDSM, their security are based on the hardness of cis, which can be reduced to the hardness of approximate SVP. So it's necessary to get a good understanding of this lattice problem, like shortest vector problem and the approximate versions, the unique SVP, the approximate SVP, to give a more accurate estimation of hardness of lattice-based schemes. Meanwhile, American National Institute of Standard Technology, they announced BKZ standardization in 2022, and the 3 over 4 candidates are lattice-based candidates. They are crystals, Kyber, crystals, DDSM, and Falcon. The security of lattice scheme based on the hardness of lattice problem. Well, the difficulty of lattice problem are based on the shape of the inputting lattice spaces. In cryptography, we will give a very bad lattice space. A lattice has infinity different kinds of lattice spaces. There are good one, there are bad one. And then we can translate a good to a bad by using randomized transformation. Is quite easy to do. But if we want to recover a good lattice space from a bad lattice space, it's very hard, and we need some powerful tools in lattice space cryptanalysis. An important invariant of lattice is its volume. Different bases of the same lattice has the same volume, and geometrically it equals to the fundamental domain of this lattice. And just like this figure shows, different bases of the same lattice, they actually have the same area. This green line, a good lattice space, and this red line, a bad lattice space, the area is the same because there are only different bases of the same lattice. The value is the same. However, the only difference is the slope. A good lattice has a very flat slope, and the bad lattice space has a very steep slope. To solve approximate SVP and unique SVP, the main tools use lattice reduction algorithm like BKZ to improve the quality of lattice spaces. And we can see from this figure that these blue lines, the slope can become more and more flat by using more and more tools of reduction of BKZ algorithm. They were gradually approaching this flat red line. And that's our job. We are trying to analyze reduction effort of BKZ reduction algorithm. And to do this, based on Gaussian heuristic, many BKZ simulator has been proposed. They are polynomial timed algorithm, and they can simulate the behavior of exponential time, the BKZ reduction algorithm, at least the exponential time. However, they are only the simulator algorithm. They cannot provide the accurate theoretical estimation of BKZ reduction algorithm, and they cannot give the number of tools needed for convergence. Based on dynamic system, many work has been done to give the rigorous theoretical analysis of lattice reduction effort of this classical lattice reduction algorithm. Like BKZ and the selected BKZ, they have been fully studied, and the number of tools needed for convergence are given by this previous work. However, there is no rigorous theoretical analysis of a new type lattice reduction algorithm, the PNG BKZ algorithm, which is quite efficient in practice. PNG BKZ algorithm was first proposed in the CPU version of JCK proposed by Martin and Amont, etc. In Europe 2019. Nice work. And this algorithm is quite efficient, and it actually broken many records in chill-domiciled LW challenge by using some optimized block size and jump selection strategy. And it's actually much faster than the when we use the optimized block size selection strategy and block size and jump selection strategy based on PNG-BKZ simulator. It's even faster than the default LW solving strategy proposed in Jessica. So we are trying to study the reduction effort of this new type, this efficient lattice reduction algorithm, this PNG-BKZ algorithm, and give more rigorous theoretical estimation of it. Here we mentioned the PNG-BKZ algorithm is actually named the pump and the jump BKZ algorithm, which is a BKZ type lattice reduction algorithm, and it uses pump as its SVP oracle. But it was mentioning that this pump can insert more than one short vector into the projected sublattice, rather than output of one short vector. So the output of a pump is a nearly educated reduced lattice spaces. And pump has two steps. It will run in progressive sieving during the pump up stage, and during the pump down stage, it will insert more than one short vector into the projected sublattice. And then it will output a nearly educated reduced lattice spaces. PNG-BKZ can perform pump with the adjustable jump value, jump value j. Especially if we run a PNG-BKZ with jump value j, that means after executing a pump on a projected sublattice whose first index begins from I, then the next pump will be executed will be the projected sublattice whose index begins from I plus j rather than I plus 1. It is the main difference between the jump BKZ and the classical BKZ. And that's our main goal. We try to construct the dynamic system of PNG-BKZ algorithm, which can help us to analyze the rigorous theoretical outbound of this algorithm and the number of tools needed for convergence. We will use the center pair model to analyze PNG-BKZ algorithm. Although the output of a pump is very close to educated reduced lattice spaces, but it's still not strictly educated reduced. So we will not focus on this this version used in practice, and we will just assume that a pump can output a strictly educated reduced basis. Based on this assumption and on the center pair model assuming proposed in HPS 11 and the Stirling's approximation, we can give this, we can express how the length of Gramish vectors, how they changed after one-to reduction of PNG-BKZ by this equation. And based on this equation, we can prove lemma 1, which shows how the length of Gramish vectors changed after the first pump's reduction. And we can say we use in equation 7, we use the old length of Gramish vector to represent the new length of Gramish vector, the left part of this equation. Then based on equation lemma 1, and we can inductively calculate how the length of Gramish vector, how it changed after any beta dimensional pump reduction, which can be triggered on different position kappa by using equation 9. But this equation is too complex to analyze, so we just express this complex equation by using a linear transformation. We set vector x to represent the length of Gramish vectors, and we got we just use this formula. Use the old length Gramish vectors, how they changed after alpha pump's reduction, here matrix A equals to this value, and the vectors A are some constant vector. Thus, we express this complex reduction process of pump. Any pump, it can be triggered on any different position by using this linear transformation. Then we consider the pump can be will be triggered on different position of kappa during one-to reduction of PNG-BKZ. We consider them all together. Then we give the dynamic system of PNG-BKZ algorithm by considering all this pump. Here is the form of the dynamic system of PNG-BKZ, and the matrix A equals to the matrix product with different matrix AI multiplied to each other, and the vector C equals to this complex result. Here we just give the recursion formula to represent the matrix A, but we didn't give the exactly form of matrix A. It's easy to calculate this matrix product with first two or three matrix AI multiplied to each other, and we can if we set the J matrix to represent all a matrix with every entry is equal to 0, and the 0 matrix is 0 matrix. I matrix represents the identity matrix. We got this result, and we can inductively calculate the matrix product with k different matrix AI multiplied to each other. It's equals to this value. So last we got the form of dynamic system of PNG-BKZ. It has two different cases of this result. According to the parameter of PNG-BKZ, the dimension d value, and the block size beta, and the jump value j. When d minus beta equals 0 mod j, we got matrix A, this value. And when d minus beta unequal to 0 mod j, we got matrix A equal to this value. After we got the form of dynamic system PNG-BKZ, we can give the solution of this dynamic system. We can prove vector x belong to this space if it satisfies the following relationship, and is sufficient to find the one solution for this equation to obtain all the solutions. Combined with lemma2, we can give the solution of the dynamic system of PNG-BKZ, just this x bar represented by the equation 12. After we got the solution, we can give the upper bound of the shortest vector output from a fully PNG-BKZ reduced basis by proving lemma 3 and lemma 4. We just got the upper bound. Here comes to a natural question that did this dynamic system of PNG-BKZ well converges, and if it does converge, it converges to the solution we gave it before, and what is the convergence speed? To solve this problem, according to the principle of power iteration algorithm, the asymptotic speed of this convergence of this sequence is determined by the eigenvalue of this matrix product. This matrix, and if this eigenvalue is smaller than 1, then this dynamic system will converges. In fact, the largest eigenvalue of this matrix product is 1, and we will show it that the second largest eigenvalue is smaller than this value. So this sequence does converges. Here is our proving process. We firstly, based on the dynamic system of PNG-BKZ we built before, the form of matrix A, we prove lemma equation 19, which is a recursion formula of this matrix product. Then we prove lemma 5, which gives the recursion formula of this characteristic polynomial. Then lemma 6 calculate the first j terms of polynomial. Finally, based on lemma 5 and lemma 6, we use Chebyshev polynomials of a second kind to to prove lemma 7, which gives the upper bound of the second largest eigenvalue of this matrix product. It's smaller than 1, so it does converges. Then we, based on lemma 4 and lemma 7, we give our main result, the theorem 1, which describes the upper bound of the shortest vector output from a fully PNG-BKZ reduced basis. and the number it needed for convergence. And we also proved that the output of PNG-BKZ does converges to the solution we gave before. We bound their distance. Then we compare with others work. We give the first theoretical estimation of PNG-BKZ by using dynamic system. Of course, based on assuming that pump outputs educated reduced basis. And we can see from this table that PNG-BKZ algorithm has an extra parameter, the jump value, which can trade off the time cost and the reduction effort. With big J, it will cause smaller number of SVP oracle during one-to-one reduction of PNG-BKZ. So the time cost is smaller. Meanwhile, we can see with big jump, the upbound of the shortest vector output from a PNG-BKZ algorithm is bigger. So big jump, smaller time cost, but worse reduction effort. It actually makes PNG-BKZ algorithm become more flexible during the reduction to prove the quality of lattice spaces. And here's some verification experiments. We can see after running enough tools, reduction of PNG-BKZ, the actual experiment volume are smaller than our theoretical upbound. And they actually are quite close. So we think our estimation is accurate. And here are some open questions. Can we remove the ideal heuristic that the pump output educated reduced basis at the very beginning? Because in practice, it is not a strictly educated reduced basis output from a pump. And can we give a more tight upbound estimation or more tight number of tools is needed for convergence of PNG-BKZ? Because we during our proving we relaxed the bound to make the proof easier. That's all. Thank you. Any question?
We have time for a few questions.
Hi, thank you for the talk. This assumption or heuristic, has this been used before, and how well, has it been analyzed?
What assumption you mentioned? Oh,
Outputs.
Educated reduced lattice spaces. It is a property of lattice spaces. Yes, I didn't show it in this slide. I can talk later if you want. It's hard to comply. It's complex to express.
Thank you for the talk. I was wondering, so if you had a big lattice to reduce, which is the sweet spot for the jump parameter? Which J would you pick?
I pick. You mean the verification?
Yes, you said there's a trade-off, right, between runtime and how strong the reduction is. So that is there a sweet spot that
1/J. Bigger jump, a big jump, it will cause 1/J times SVP oracle during 1-2 reduction.
Yeah. So but is there a
I mean,
but if you had to solve a challenge using this, which jump would you select?
That comes to another question. We give another paper about how to optimize the best choice of block size and the jump selecting strategy. We use different measures to find the optimal parameter to make making it more efficient. And this paper haven't accept, but we submit to ePrint. And how can I say? Another paper already accepted by PKC this year. You can check it.
We have time for one last question. Okay, well, in this case, let's thank Lei Zhang again.